Welcome back. In this video, we're going to be talking about applications of trig functions, which basically means this is a video about word problems that involve trig functions. And we're going to start things off just for a few minutes talking about inverse trig functions, and we'll pull out the calculator and find some angle measures of a given triangle. And this is our last conversation, excuse me, in an entire chapter which has been about trig functions. So we'll be changing gears a little bit if you're following me on to the next video, but for now let's get started looking at some applications. The first thing you're seeing at the top of this page is very familiar to you, and it is SOHCAHTOA. So we have sine being opposite over hypotenuse, cosine is adjacent divided by hypotenuse, and tangent is opposite over adjacent. When you started this adventure, maybe that was new information to you. Now it's old news, boring, hopefully anyway. And these instructions, solve the right triangle, are asking us to essentially find all missing information, any missing side lengths and any missing angle measures. And we have a bunch of missing angle measures. So let's get started. The first thing I think we should do is find the missing side length, and that one's pretty easy. It's a process that we're familiar with. We'll use the Pythagorean theorem. So we have a squared plus b squared equals c squared. We don't know what our a value is. B is 4, we'll square that. C is 9, we're going to square that. And these are not going to be great numbers. A squared plus 16 equals 81. Ugh, that means I have to do subtraction. I should have gotten my calculator out in advance. A squared equals 81, 71, 65. We're looking at 65. And 65, you don't have to write this down. It's kind of a lousy number. Let's see, 65 is definitely divisible by 5, and 5 goes into 6 once. Carry the 1, which makes a 15. 5 goes into 15 3 times. It's 5 times 13. Those are already prime numbers, so this is the prime factorization. You might remember that phrase. And the reason I did that is to make sure that we couldn't simplify in our next step, which is when we take the square root of both sides. And we're going to get a is equal to the square root of 65. It's not like, the square root of 12, which we can write as the square root of 4 times the square root of 3, and then we simplify it and we get 2 root 3. That was nice because the 4 was square rootable. Neither the 5 nor the 13 are square rootable, and so we're stuck with those. So let's keep going. You can leave this out. Let's keep going using an a value of the square root of 65, and that would be one of our answers. We'll leave it in radical form when we type it in. Don't use a decimal approximation unless you're asked to. And if you're filling in these principal notes, or if you've redrawn this diagram for yourself and you want to write in the square root of 65 on the diagram, that's a fine idea. And maybe I'm going to put in these other side lengths as well. Okay, now we need to find some angle measures. And in order to find the measure of angle A, I'll switch colors here. I think I'll use the sine function in order to find the measure of angle A. So let's see, the sine of capital A is equal to, now that's opposite divided by hypotenuse. So that's the square root of 65 divided by a hypotenuse of 9. In order to get rid of the sine function from the left-hand side of the equation, I can't divide both sides by the sine function. I need to take the inverse sine of both sides. So I'll write this out one time, and then we'll shorten the process a little bit, excuse me, as we find our other two angle measures. But here I'm literally taking the inverse sine, and you're seeing it written on both sides of the equation. I'm taking the inverse sine of both sides. Now on the left-hand side, the inverse sine and the sine are going to cancel out. We know that we're working with a legitimate triangle here, so I don't have to worry about any restricted or domains of restricted trig functions, or however you'd like to phrase that. I know that the inverse sine and the sine are going to cancel out, so I'm left with a equals, and I'm going to maybe even put a little sort of squiggly equal sign to indicate that this is going to be a decimal approximation that I'm going to put on the right hand side I don't have my calculator. I'm not very prepared. Thankfully, it's just in the next room. Let me grab that. All right, so at this point, in my class with my students, I'm not allowing them to use graphing calculators. And there are reasons for that. We don't need to talk about that. So I'm going to be evaluating the inverse sine on my TI-30XA single line entry scientific calculator. If you have a scientific calculator that has two lines of input, one above the other, then evaluating the inverse sine is pretty easy. You can hit the second button on your calculator and then the sine button, which should give you an inverse sine on your screen, probably, and or I should say, and it'll probably give you a parenthesis also. And then you can type in literally the square root of 65, and then you might have to arrow over or something when you do the divided by 9. So as you're typing this in, make sure that the division by 9 is not occurring under the square root symbol. So this is maybe the one time where this particular calculator is going to be beneficial, because it's really easy to avoid accidentally square rooting the division by 9. So let's type it in on this calculator. I'm going to, now this thing's weird, we have to sort of work it from the inside out. So I'm going to type in 65, and then I'm going to hit the square root button, if I can find it. There it is. And I get 8.06225, etc. And I'll leave that on the screen, hit divided by 9 equals, and I've got 0.895. And then I'm going to hit my second button, and then the sine button for inverse sine, and I got 63.61. Now, I didn't say this in the beginning, I just suppose I got lucky, because my calculator was already in degree mode, so that is 63.61 degrees. If you got something other than 63.61, you might be in radian mode, so go through those motions again after changing your calculator into radian mode. If you're using this calculator, don't forget that the near the top there's a DRG button, and you can hit that a couple of times to scroll yourself around back into degree mode. If you were in radian mode, you'll have to hit it twice on this calculator. All right, so let me write this down, 63.61. And maybe I'll put a box around my lowercase a value, and then I'll put a box around this capital A value. And then let's get set up to find capital B. And let's actually use the cosine function this time to find angle B. The cosine, oh, let me switch colors just so it's easier to differentiate between one part of the solution process and the other. So I said let's use cosine, and if we're using cosine of the angle of B, now cosine is adjacent divided by hypotenuse, and that's root 65 divided by 9 also. We didn't have to use cosine. We could have used the, we didn't have to use cosine. We could have used the sine of angle B equals 4 divided by 9, and then we would be taking the inverse sine of both sides of that equation. But I thought let's mix up the trig functions. All right, so now I'm going to take the inverse cosine of both sides. If you use this little notation, cosine inverse, right? Sometimes I put a little note in the margin about what I'm doing to both sides. Taking the inverse cosine. On the left-hand side, the cosine and the inverse cosine cancel each other out, leaving us just with the b value. On the right-hand side, I do still need to take the inverse cosine of the square root of 65 divided by 9. And now I'm going into my calculator, clearing first. I'm in degree mode still, yep. And I will take type in 65 and then square root divided by 9 equals, oh, I sounded very robotic there. I'm using a calculator, I guess that's okay. Right, so I've got 0.8958 on my screen. I'm going to hit second and the cosine button this time in order to take the inverse cosine. And in degrees, I've got 26.39. Squiggly equals 26.39. Now, in order to find the measure of angle C, we could use... We don't need to do anything in order to find the measure of angle C. In this case, we're working with a right triangle still. So we know what the measure of angle C is, which means the inverse trig work that we just did was a little bit silly, because we could have done 180 degrees minus 90 degrees for angle C, minus 63.61 for angle A, and we would have gotten this B value of 26.39. But good to practice with the calculator, typing it in, using the inverse trig functions, and making sure that we know how to do that. There will come a time in the not too distant future when we're working with the law of sines and the law of cosines, where we will work with triangles that are not right triangles, and we will still bring the trig functions to bear on those triangles, and we will need to use inverse trig functions to find two angle measures, and then we can subtract from 180 in order to get the third one. But that third angle measure is not always going to be 90 degrees. Did we find it? Yep, the initial problem gave us two angle measures, or sorry, two side lengths of 4 and 9 and one angle measure. So we found two angle measures and one side length. Perfect. That's it for that one. All right, a real application problem. The flagpole is situated on top of a building. Well, I guess I don't have to read it out loud. You can read it. All right, so we're going to need to draw ourselves a diagram because in this problem, one was not provided for us. So here's the ground, and here's the building, and a beautiful one at that. And here's my flagpole. And let's get a flag on there. We've reached that point already. 12 minutes and 46 seconds. Let's see if that's a consistent thing, that the iPad takes its little siesta. There we go. And let's get a flag on there. Now, there's a point on level ground 330 feet away from the building. And let's go ahead and put ourselves there. And we can label that as 330 feet. That's two F's. That doesn't work that way. There we go. And the angle, of elevation from that point to the top of the flagpole is 63 degrees. So from this point up to here, this angle measure is 63 degrees. From the same point to the bottom of the flagpole is 53 degrees. So I'm going to label this one with the 53 degrees. And if you can, depending on how sharp of a pencil you're using to take your notes, maybe you can sneak a 10-degree measure in here. That is awfully small by the time I zoom out. And the question is asking us to find the height of the flagpole to the nearest tenth. Okay. This is going to definitely be a two-step process. And it's my guess that we're going to need to find, let's see, we're trying to find the height of the flagpole. It's my guess that we'll need to find the height of the building, and then using the larger triangle with the 63-degree angle measure, we'll find the total height from the ground to the top of the flagpole, and then we'll do subtraction in order to find the height of the flagpole. Let's see if that works out. Maybe we could label the height of the building with a lowercase b, and the total height maybe with a lowercase t. And we could definitely label the height of the flagpole with a lowercase f. I think that works. If it doesn't work, we'll change them. Now, let's do a little trig. I need a trig function that relates the 53-degree angle measure to the horizontal distance of 330 feet, and the height of the building, so that's like a vertical leg of that triangle. I'm going to put a right angle in there, lowercase b. That's the opposite side and the adjacent side, so I think we're looking at using the tangent function here. So the tangent of 53 degrees is equal to opposite, which is b, divided by adjacent, which is 330. That's a 0. There you go. And, oh, this is nice. All we have to do is multiply both sides by 330, and we will have our b value. Nice. So 330 times the tan of 53 degrees is equal to b. And then we'll jump into the calculator. Make sure, again, that you are in degree mode. I think I still am, yep. So I'll clear a couple times. And again, on the TI-30XA, I'm working this thing from inside out, which means I'm typing in the 53 first, then hitting tangent. I've got 1.327, and then I will multiply by 330 equals, and I have 437.92 is approximately equal to my b value. All right, then let's go through a similar process and see if we can find t. This time, the tangent of 63 degrees will be equal to opposite, which is t, divided by adjacent, which is the 330 again, and we'll multiply both sides by 330. And we'll get our t value. All right, back to the calculator. I've got 63 tan, that's 1.9626 times 330 equals, and I got 647.66. There's our t value, and then in order to finally solve for the height of the flagpole, we'll find the difference between those two values. Lowercase f, I was calling it in my diagram, is equal to the total height t minus b, the height of the building, which is equal to 647.66 minus 437.92, which is equal to, I've already got the 647.66 on the screen of my calculator, so I'm just going to hit the minus sign. 437.92 equals, and I got 209.74. And let's see if there were any specific instructions about rounding. Find the height of the flagpole to the nearest tenth of a foot. Good thing we were taking it out to 2 decimal places. Now we can round it back to 1, so I'm calling it 209.7. And that's feet. And that's a 20-story tall flagpole. That's a big flagpole. That flagpole is 209 feet tall, and what was the height of the building again? 437 feet. I wonder if that's realistic. Would you ever have a flagpole that's half the height of a building? If your building were 10 feet tall, a foot tall flagpole sounds reasonable. 40 stories tall? Let's do a little research one day and see if that's legit. Can we find a building that's 400 feet tall that has a 200 foot tall flagpole on it? I'm suspicious. So we'll change gears a little bit here and talk about bearings. And these are fun. I like these. It's almost a bit of a puzzle or a game. It's considerably more fun, of course, when you're getting right answers, but it's nice because it's quite visual. So bearings are used in navigation, and when you give somebody bearings, they have 3 parts. There is going to be some indication of whether you're going north or south, and then there's going to be an angle measure, we'll call it theta, that's going to be between 0 degrees and 90 degrees. Strange that we've switched back to degrees in this section. We've been working with radians so much, but degrees for a little while. And then last, we will have an indicator of whether we're going east or west. And here are some examples. These are very helpful. On the left here, we've got a bearing that says north 40 degrees east. And the way that I always envision this happening is, and this little sort of swooping arrow that you see here matches up with this description. I imagine that I'm starting out aiming north, which is sort of up, and then I rotate in the easterly direction 40 degrees. So north, and then rotate 40 degrees toward east. And then you'll move in that direction, and then hopefully the problem will give you some amount of distance that you're to travel. Second example, we're starting out aiming north again, but this time we're rotating 65 degrees toward west, and then we will proceed in that direction. And here, in order to get into the 4th quadrant, we start out aiming south, and then rotate 70 degrees, in this case, toward east, and then off we go. All right. I'm just tweaking my screen a little bit. I like that. All right, so let's see if we can get... Can I move me in the corner there? Why is that happening? Why can't I grab that? All right, I'll leave it there. An example problem using bearings. So a boat leaves the entrance to a harbor and travels 40 miles. So there's our distance on a particular bearing, south 64 east. How many miles south from the harbor has the boat traveled? So let me paint this picture for you. We're going to go south and south 64 east. I don't like this because I don't need all 4 quadrants. Why would I draw this thing with 4 quadrants? Strange. So I'm going to start out aiming south, and then I'm going to rotate toward east 64 degrees, so I'm going to end up going this way. I knew that already, so I'm going to erase that. So I know that I'm going into the 4th quadrant. So let me draw just the 4th quadrant. And then we're going south, rotating 64 degrees toward east, which is more than 45 degrees. It's pretty close to 60, so I'm almost drawing this like the way my things are set up over here is making it awkward for me to draw this. All right, that is our path of travel, and this measure right here is the 64 degrees. And south is down here, and east is over here. And what I'm going to do is I'm going to make this problem more comfortable for me. I'm going to make this look more like a situation that I have worked with in the past. And in order to do that, I'm going to draw this sort of vertical leg. I'm even going to put an arrow at the bottom of it. And and then I'm going to label this reference angle in here as 26 degrees. Now this matches up more with the way that I learned about evaluating trig functions and finding those radian measures on the unit circle, etc. Excuse me, and I'm going to label my hypotenuse with a 40 because the problem told me that we traveled 40 miles. So maybe I'll put a little mi for miles on there. And the question goes on to ask, how many miles south from the harbor has the boat traveled? So south is in this downward direction, and I'm going to label my red leg of my triangle here with a y, since it's moving in the y direction. And now I can use the processes that we've been using already in this video in order to solve for y. So looking at the 26-degree angle measure, I've got an opposite side length of y, a hypotenuse of 40, so opposite over hypotenuse. That is the sine function. So the sine of 26 degrees is equal to y over 40. Multiply both sides by 40. Grab the old calculator, typing it in from inside out on this one. So I'm clearing a couple times, still in degree mode, yep. 26 sine, I've got 0.438 times 40 equals, and I got 17.53. And that is our distance in the southerly direction. And the next thing that we'll do is we'll finish solving for at least the side lengths of this triangle, and we'll find how far to the east our boat has traveled in its 40-mile journey. To the east, let's go ahead and continue doing some good labeling on our diagram. There we go. So in the x direction, the horizontal direction, which in this case is to the east, we don't even have to move away from our already known angle measure of 26 degrees. I'm just going to slide over to the right a little bit here, and I'm going to use the cosine function in order to find my x value. So the cosine of 26 degrees will equal adjacent, which is x, over hypotenuse, which is the 40 we already know. Multiply 40 to both sides, so that the x is all alone on the right-hand side. Back to our trusty scientific calculator. I've got the 26 going in first in degree mode. Cosine, I've got 0.89879 times the 40 equals, and I've got 35.95. And that's miles. So that's, we can just say equals x. Put a little mi in there maybe for miles. And that's our movement to the east. Now this question did not ask for how far to the east is the ship from the entrance to the harbor, or since the ship was leaving the harbor, I guess that makes it an exit also. Good news is that when we continue on, is this going to zoom out? Yep, there we go. When we continue on to the next page, we are asked how many miles east from the harbor has the boat traveled. So we've already determined the answer to that. I knew that was coming, but to just continue working next to the diagram seemed to make sense to me. So all that work is up there. If you want to put a little note on here that says see previous page, you may. And I'm going to be saving this problem to do with my students in class. I may come back and make a separate video of that one. This is a good one. So if you're one of my students and you want to try this in advance, I welcome you to. If you're not one of my students, I still encourage you to give this a shot. And the real challenge to this problem is determining whether or not the ship ends up in the second or third quadrant. So if you do this problem correctly and you draw your diagram with some pretty decent amount of accuracy, you should end up with a bit of a question mark of whether or not your ship is going to end up in the second or third quadrant. And then trying to figure out how to make that determination is a little challenge. And finally, you'll need to make that determination in order to decide how to answer the question, because you will either be answering north, rotating to the west, or you'll be answering south, rotating to the west. It's like I'm a little teak. How does that go again? Anyway, a little tricky, so you should try that one. And then here we change gears again for the last couple of pages worth of these notes. Here we're talking about simple harmonic motion. We're using equations that look very familiar. So it's just sine and cosine, possible modifications to amplitude, period, and phase shift. You're not seeing a d value at the end. In this particular application, there would not be a vertical shift, although in a way there already was one, but we take it out of the equation literally. Everything that you're seeing here you're already familiar with, which is really nice, except it's in different colors this time, which I like. And this part of the diagram is different. And let's look at this just a little more specifically. So this is just an example. And what's happening is, on the left you see this d is equal to 0. And that's sort of a resting point. So this is a mass that's hung at the end of, or attached to the end of a spring, at the bottom of a spring. And in this particular example, when time is equal to 0, the mass has been pulled downward a distance of 4 inches, probably, something like that. And then right when the stopwatch starts sort of keeping time, and we're marching through our time values as we go from left to right, t equals 1, t equals 2, and so on, the first thing that the mass does, because we started out by pulling the spring or pulling down on the mass, is it's going to move in the upward direction. And you see this sort of wave that it generates as it passes through time. So that, of course, looks like a sine or a cosine graph. The question would be, which one of those two functions should I use in order to model what it is that we're seeing here? And I think the answer will become pretty clear if we consider this to be the x-axis. If that's the x-axis, then our mass, this ball that we're looking at here, has not started at the origin. The basic sine graph, when we look at it, because it does pass through the origin naturally, the basic sine graph sort of starts at 0, 0. This graph, the path of this object, is not starting at 0, 0. So that compels me to probably use the cosine graph in order to model what we're seeing here. The cosine graph, of course, starts above the x-axis at 1. And here, we're not even starting at 1, we're starting at positive 4. So this would be a transformed cosine function. You'd have an amplitude value of positive 4 if we were starting above the x-axis. Here we're starting below, so I would use a capital A value of negative 4. And then we could go through and dissect this more and talk about how to modify the equation further in order to account for the period of this graph. But since there's no prompt, and there's no room really to take notes around it, I'm going to keep going. We will see an example. But first, let's take note of a couple of variations that we might see in notation. On the left side, instead of a y value, we're seeing a d value, and the d is the distance from the origin. You could also think of the d value as displacement, because the graph that's at the top of the screen right now looks like the ball is moving from left to right. It's not. It's just bouncing up and down, except it looks like it's moving from left to right in this depiction because the horizontal axis is the time axis. So it is moving forward through time, but it's not moving forward through space. It's just moving up and down in space. So displacement makes sense. The a value here is a lowercase a. Doesn't really look like an alpha to me, so I'm going to call it an a. Cosine wt, that lowercase w does look like a lowercase omega. I'm not sure why the election is made to use that instead of a more sort of normal looking w. T definitely makes sense because we're moving through time. Based on this notation, the amplitude, we can still answer that, and I would still answer it with the absolute value of whatever that leading coefficient is. The period, because we're working with sine and cosine, will be calculated by taking 2 pi, the original period of the sine and cosine functions, and then we'll take that and divide it by this sort of w-looking value. And then there's the frequency, and the frequency is not something that we have been asked for previously. The frequency, what's frequency? Like revolutions per minute. How many occurrences are happening within one particular measure of time, for example, is sort of one way that we could look at frequency. And as it happens, frequency is the reciprocal of the period. So if you're asked for the frequency, you can calculate the period and take the reciprocal. As we were talking about when we were looking at the diagram of the mass attached to the end of the spring, we're going to use the cosine function if the object is at maximum distance when t equals 0. And we'll use the sine function if the object is at rest when t equals 0. So if you attached the mass to the end of a spring, certainly the mass would cause the spring to descend a little bit, but then it would stabilize and it would rest just there before you finally walk over and perhaps give it a push in the upward direction in order to initiate some sort of oscillation, or you could grab it and pull it down and then let go in order to initiate motion. But that's what I mean by at rest. It means we've sort of let it settle at the end of the spring, and that's where our stopwatch would start with a time value of 0. All right, and this is one of 2 examples that we'll look at. An object attached to a coiled spring, much like in the diagram that we were just looking at, is pulled in the negative direction, like the diagram, from rest and then released, just like that diagram. Write an equation for the distance of the object from its at rest position. So, as an equation for the distance of the object from its at rest position. In the diagram that we saw above, we saw when time was equal to 0, d was equal to -4. So the negative means that we were below the at-rest position, and the 4 told us how far below the at-rest position. Here we're going to be pulled in the negative direction, it says in the first sentence, and we're seeing in this little table a distance of 8 inches, which gives us an amplitude of 8, certainly, and then a period of 2 seconds. So you don't have to draw this, but if we just look at this together, we're starting 8 units below the at-rest position, and we're going to model this using the cosine graph. So I am drawing my way through time here, and what I've just depicted is 1 period worth of our function. So the period is equal to 2 seconds. So I could label that with a 2. Now when we talk about frequency, if the period is equal to 2, what's the frequency? The frequency would be the reciprocal of 2. Now 2 seconds. Before I keep going with that, the period is 2 seconds. What happened there? We got one. It's not really a full rotation. It's one oscillation, right? It started below the x-axis, and then it went up, and then it maxed out, and then it came back down to its initial sort of location, 8 inches below the at-rest position. So that was one oscillation, and I'm not going to try to spell oscillation. So that was one cycle per, and then how long did it take? 2 seconds. So that's a way that we can see how the period, or rather the reciprocal of the period, comes to describe the frequency. We've got 1 cycle per second. In other words, it's a half of us. So the other way that we could write this is 1/2 cycle per 1 second. So per second. In 1 second, how much of a cycle did we go through? How much of an oscillation? In 1 second, we only made it a half of a cycle. So that's frequency, or at least my attempt at describing the relationship between period and frequency. All right, let's write ourselves a quick equation. This will be the easy part, instead of trying to understand what the heck I'm talking about. We'll use d equals lowercase a. We're going to model this one using cosine. We've got this little omega value times t. We said we're starting with a displacement of 8 inches in the negative direction, so my a value is going to be a -8 cosine. And then we need that w value. So we know that period is equal to the original period of 2 pi divided by our omega value, or our w value, or the b value. This problem tells us that the period is equal to 2 seconds, which is equal to 2 pi divided by whatever that w value is. Let's solve for that w. We need that. I'm going to multiply both sides by the w, so that I have 2w is equal to 2 pi, divide both sides by 2, and we have that w is equal to pi. So we can plug that into this equation right here. If you want to put the wt in parentheses and have it be a pi t, you're welcome to do that, but that is the equation that models the motion that's being described in this example problem. I like when they give us all the information we need right in a table. Makes the process much easier. Let's do this backwards now. Here we're being given the equation, and d is being measured in inches, t is being measured in seconds, in case it was a free response question where you were required to include units. The maximum displacement excuse me, will be equal to the absolute value of our a value, which in this case is the absolute value of a +3, which is 3, and it's a distance being measured in inches. The time required for 1 cycle, for 1 full cycle, not a half of a cycle, okay, like we ran into in the previous problem. And I know that part B here is asking me for the period because part C is asking me for the frequency. So I'm glad that that was there so that I make sure I'm answering the correct question. So the period here is equal to 2 pi divided by the omega value, or the w value, or the b value, which is 2 pi divided by, I see that pi symbol attached to the t in the original equation. Am I looking in the right direction? I am. All right, so that is a pi. Pi's cancel, and we get 2 seconds. And then the frequency is the reciprocal of that. So that's actually 2 seconds per cycle. And the frequency is the reciprocal of all of that mess, which would be the reciprocal of 2 is 1/2, and then seconds per cycle becomes cycles, or 1/2 cycle, I suppose, per second. And the phase shift of the motion, because inside of these parentheses up here, right there, inside those parentheses, no factoring has been done already. There's no square brackets and then some additional set of parentheses inside of there. None of that's happening. So we do indeed have to, take C and divide it by B. So the phase shift here is equal to, I'll give you a moment, what's your C value that we're going to use to calculate the phase shift? Hopefully you said it's -π/2. We'll have to divide that by the B value of pi. If you want to think of it as π/1, you can. That's equal to -π/2 times the reciprocal of pi, which is 1/π. The pi's cancel, and we have -1/2. So our phase shift is -1/2. What do you think about units on that one? That's a tricky one. What would the units be? Well, t measures time. Cosine, that whole thing's got to be time. π/2 must be measured in terms of time also, right? Because here, look with me right there. This t value is definitely measured in seconds. So that's got seconds covered. So the pi value next to it doesn't need to be measured in seconds because the t value is already measured in seconds. But you'd want to make sure to add seconds plus seconds, so I think that this π/2 right here must also be, why didn't I draw that many? That π/2 right there must also be measured in seconds, which means that this π/2, or -π/2 really, must be measured in seconds. And the pi that we divided it by is right there, that pi value next to the s. That pi didn't have any units, we said. So the phase shift, does that make sense that it's a horizontal shift measured in seconds? What was this horizontal axis measuring? Time in seconds? I think it was. What was this horizontal axis measuring? Time? Perhaps in seconds? I think we got it. That was a nice little bit of investigation that I think brought us right to the right spot, the right conclusion, that that phase shift of -1/2 is indeed measured in seconds. Nice. Hey, thanks for joining me. That was a nice variety of topics that we got to see. The iPad's already blinking, so that must mean that it's time to go. I'll see you next time. Thanks so much.